you know. Okay, so for you guys online, the problem we're talking about is on some Mac installations, when you try and paste a graphic into Word, it doesn't appear in Word. It's really there, it's just you can't see it. So if you go into, you change from the normal view, which is called draft, that's usually the way it opens up. You would type and so on and so forth. If you change from there into the print layout view, that's a version of it that shows you, what you see is what you get. Like, in other words, what you're seeing there is you can actually see the end of the page and the next page and so on. So it's a pretty convenient way to work anyway. But in that version, if you paste it in there, it seems to work. Copy and paste. Most of you guys have no idea what I'm talking about, and that's a good thing, because that means you didn't have the problem. I still have not found a solution to saving files on the virtual desktop version to my local computer. Have you guys been successful at that? Have you guys tried that? How about it online? Anybody successful at saving files, working on files on the virtual desktop and then saving them to your local computer? Especially, like, for instance, the RTF files, the export RTF files. Anybody able to get that to work? I'm not getting any responses. I'm going to take that as they don't. But I think that's another thing that'll work out as time goes on, and IT gets that working. Yeah, a couple of people haven't been able to do that either. Okay, so I guess in that case you can kind of do a screen capture or something like that. Like I said, I'm not a fan of the virtual desktop version because of all the other issues with speed and lag and the possibility of crashing and losing your work and so on. So and also not being able to work without an internet connection. Yep. Yeah. Control. Yeah. Thomas, when you say Control V to paste, you mean copying and pasting into Word? From Word? Okay. So what we found is if instead of working, you see Word open on my desktop right now. What we found, if you're working in the print layout view, if you go up here to view, you can switch between draft view, which is usually what it defaults to, a web layout, outline view. You can, like, if you want to build outlines and so on. But if you work in the print layout, it'll work just like the draft version. You can type and do other stuff. But we found that if you keep it in that view, you will be able to copy and paste stuff into Word from SPSS, including the graphics. So you might want to give that a try when you get a chance. Let me know if it works out for you. Okay, so how about let's start with old business. This week we started going in a new direction. We started talking about probability, right? So I just want to make sure, anybody have any issues from before that you want to talk about? Data types or any of the other material that we worked on before this week? And maybe that. Okay, so probably we can go ahead and move up to. Most of you guys have already submitted the homework and so on and so forth, so you've had a chance to play around with this. So let's move on to probability. Okay, before I start, any questions from what we did, from the lecture, if you got a chance to watch it, or the lab recording, if you got a chance. You got any questions off the top of your heads? Because I'll start reviewing it if you don't have a specific question you want to bring up right now. Okay, you can be timid. It's okay. As I go through it, just yell at me and get me to stop. You guys keep an eye on me over here. If you see people saying stop for a second, I have a question on the chat box. Warn me so in case I don't see them mentioning it. Okay, so let's look at the basics here in terms of. I just want to look at the graphics if I can find some graphics if I can find it. It must be the first day of fall, right? Is that why they have that image on there? Okay, whoops. Okay. Okay. I just want to get that graphic on here in case I need it. Okay, so let's talk about probability, the likelihood of a certain outcome. basically, we can kind of look at that as, well, we can look at, and one of the ways we can look at that is in terms of the likelihood of how many different events you might have. You know, if we have an exhaustive list of all the events that might occur, the total number of events that might occur. Whoops. Oh, I have a problem here. Houston. Let me try again. Oh, I'm using the back of the pen. There you go. Flip it over. Okay, total number of possible outcomes. Right? And over the top of this, we're going to have the outcomes we want. Outcomes that we're interested in. Well, what do I mean by that? Let's say you flip a coin. How many possible outcomes do you have when you flip a coin? Equally likely outcomes do you have when you flip a coin? You got two, right? Right? And let's say you're interested in heads. There's one outcome out of the two that you're interested in, right? So the odds is 1 to 2, or 1/2. The probability of getting heads is 0.5. Okay, how about if I have a die or a dice, right? How many possible outcomes do we have for a die? 6, right? Let's say the outcome that I want is 4, right? If I want that specific outcome, there's only one way for that to happen. So the odds, the probability of that happening is 1/6. And part of the issue here is, part of what we have to recognize here is that all the possibilities are exhaustive. In other words, there's only 6 possibilities, and we included all of them. They're independent. If you throw a die one time, it's going to be not going to remember. It's going to be different the next time. And the probability of each outcome is the same. 2 is as likely to come up as 4 is, and so on. Right? Okay, how about if I say that I'm going to toss a die, and I'm willing to accept as the value I'm interested in is anything that's equal to or less than 3. Okay, how many possible outcomes do I have? I got I have 3 that are acceptable, right? Out of 6 possible outcomes. So that's 50-50, right? 1/2, just like the die. Okay, how about if I roll 2 die? Right? Well, if I roll 2 die, let me think about what's going to happen there. The first die could be a 1, and the second die doesn't know what the first die was going to be. So it could be a 1 and a 2, a 1 and a 1, a 1, and the second one could be a 2. First one could be a 1, so it would be 2. The 3 rather, a 1 and 4, a 1 and 5, a 1 and 6. There's 6 possible outcomes for that second die if I roll a 1, the first one. Well, a 2 and 1, 2 and 2. Same thing with if I had rolled a 2, I have 6 possible outcomes. So the total, if I roll 2 die, the total number of outcomes is how much? Right? You got 6 possible for the first, and each one of those has 6 possibilities for the second die. So it's 6 times 6, 36. Right, it's 36. You people go to Atlantic City every once in a while, right? You should know this stuff. Okay, so it's 36. What's the probability of a 7 coming up? Well, how many of these various ways give you that outcome? How many ways? What's that?
They add up to 7?
Yeah, yeah. How many different ways can you make a 7? 1 and 6, right? 4. Okay, hang on. Let's get. Oh yeah, 4 and 3, 5 and 2, right? That it? Yeah, that's it. Except, hang on a second. We also got to consider, if we consider 1 and 6, the first die could be 6. The second one could be 1, right? And the same thing with 4. It could be, we got 4 and 3, it could be the other way around too, and so on. And 2 and 5, right?
So, okay. So with 2 dies, you have 2 chances.
You have 2. You have 6 ways that you can make 7.
Right.
Right. Okay. You have 6 different ways that you can make 7.
That's because you have so many ways to make 7.
Right.
With the 2 dies.
And they don't know what the other one's doing, so they're independent of one another.
Is there a way to
make it come up 7? No.
No.
I've tried that, but it doesn't. Yeah, I've tried.
Is there a way to calculate this by using some kind of formula?
Well, yeah, as we go on, we're going to talk about factorials and combinatorials and so on, and a whole bunch of stuff like that. Right now, let's keep it simple for right now. Okay, so there are 6 possibilities out of 36 outcomes, right? So the odds of rolling a 7 on any particular roll is 1 out of 6. Okay, How much do you think it pays off if you bet 7 on a craps table or something like that? It's 4 to 1. Okay. It don't pay off. It pays off less than. Okay, how about 11? How many different ways are there to make 11? Right?
74.
There's no 7.
Oh,
Right.
6 and 5.
6 and 5. What else? 5 and 6. There's only 2 ways. So you got 2 ways out of 11, 2 ways out of 36. So the odds of rolling an 11 is 1 out of 18. Right? Those are the odds. What do you think they pay off on a craps table? 15 to 1. Right? So it's still a loser. You want it, if it paid off 18 to 1, it would be even money. Right? So think of it this way. For every $100 that you bet that 11 is going to come up on the next roll, right? You would win $1,500 on average, but you would lose $1,800, right? So for every $100, for every $3,300 that you bet on the average, you lose $300, right? If you kept doing it and do it, right? So there's much better bets on the craps table, but you get the idea. There are ways. What we're looking at is how many outcomes satisfy what we're interested in and how many possible outcomes do we have. Okay, so let's move on from there to the idea of how we can represent all of these different outcomes in terms of populations. I'm going to open up Blackboard. Actually, I'm going to open up the homework, and we'll take a quick look at that too. Homework assignment. Okay, we'll do a little bit of preview of the homework assignment number 2. Okay, and I'm going to continue. Okay, one of the things we're looking at there. Well, before I look at these first couple of examples, I'm going to give you a version of them. Okay, now let's take a look at. Let's say that we went back to our example of a coin. If I rolled 3 coins, what's the probability that I would get 3 heads in a row? What's the probability of the first one being a head? 1 out of 2 or 0.5. What's the probability of the second one? Same thing and same thing, right? So it's 0.5 times 0.5 times 0.5, which is 0.125. It's 1 out of 8. Another way to look at this is 1/2 times 1/2 times 1/2. And that's 1 over 8, right? Which is the same thing as 0.125. Okay, so it's pretty simple, right? If I look at it from this, all 3 events being the same, it's pretty simple. It's the multiplication rule. I can just multiply. Let's say I had a population where 10% of the population was diabetic. What's the probability that 1 person is diabetic if the prevalence is 10%? 0.1, right? 1 out of 10, 10%, not 1%, 10%, right? It's 0.1. Now, what if I randomly selected 2 people from that population? What's the probability that they would both be diabetic? 0.1 times 0.1, which is equal to 0.01. How about if I did it for 3 people? 0.1 times 0.1 times 0.1, which is equal to 0.001. 1 out of 1,000, in other words, that all 3 are diabetic. What's the probability that 2 people, that if I pick out 2 people at random, completely independent of one another, that both of them would be not diabetic? What's the probability one of them would be not diabetic? Right? 10% chance of being diabetic. If 10% of the population is diabetic, 1% of it is 90%, right? So the probability of picking out somebody that's not diabetic, if I pick out 1, is 0.92 times 0.9, or is equal to 0.81. Okay? 81% probability.
I have a question.
Yes?
Is there a rule we could use to know when to multiply?
Well, first of all, they have to be independent. Okay? So now, if you stood out, if the prevalence of diabetes in the population is 10%, but you stood out, if you went and sampled people in a healthcare facility for elderly people, right? There's a problem there. You're biased. right? Because that population now is not independent of, they're not independent. You have a population where it's more likely you're going to get people that are diabetic. Okay. The other thing is that you're assuming that there's two possibilities here: diabetic or not diabetic. We're going to get into that in a couple of weeks. That's called a binomial outcome. It could be one of two things: yes or no, diabetic, not diabetic, heads, tails, and so on and so forth. But we'll get into that. Okay, so we can use this a few ways. Okay, but we know that our expectation is if you have a population where 30% let's say 30% of the population is right-handed, left-handed, excuse me. What's the likelihood you would pick three people in a row that are left-handed? It's going to be 0.3 times 0.3 times 0.3, right? That's 0.09 times 3 is 0.027, about 3%.
Right? And that's looking at a general population.
General population. Okay. So now, what if I told you you went and sampled You went and sampled three people in France, but you didn't do it just once. You did it many times, and you found that the average outcome when you took three people at random, on the average, you found that 4% of them were were when you took your sample, if you know that the population prevalence is 0.027, right? I really shouldn't have brought up the Fred. Same population, right? Where you know that 30% of the population is left-handed. If you examined someone that was taking a sample, and it turned out that their sample suggested that the likelihood of getting three people in a row was 4%, what would that suggest to you? It would suggest to you that whatever way they sampled, they didn't sample independently. Their samples were not really independent, right? So you need to get that to if it's truly an independent sample. Okay, so now we kind of taking a look at that. Let's look at this from another perspective. Let's look at how we might represent. Let me go back in here to where the test was. Let's look at how we might represent different populations. Okay, so one of the things that we do in statistics is we represent the populations and probabilities using something called Venn diagrams. You guys ever look at Venn diagrams before this course? You've seen them before, right? In various math courses and stuff, especially if you've taken any statistics at all before. Okay, you guys online okay with this stuff so far? Okay, so let's take a look. Let's make a Venn diagram right here. Okay, so let's say that that the A represents diabetics and B represents non-diabetics. Kind of look messed up there. So I could represent that as, say, this area here represents people that are diabetic, and this area here represents people that are not diabetic. Now, they don't overlap, do they? No. Right? They're independent. They're exclusive. In other words, you're either diabetic or you're not diabetic. Okay? Well, now let's represent a different population and a different variable. Except this time, population A and population B overlap. So they're not exclusive. You could have people that are both. Both. Now, give me an example. What could A be? What could B be? Something that's not. How about A is diabetic and B is left-handed? Right? You could have people that are left-handed and diabetic, and they're represented in here. Okay. When you look at a situation where you want to include the probability of being diabetic and the probability of being non-diabetic, right? If you want to include both of those people and it's exclusive, you might represent it this way, and you would call that the union of probability of A and probability of B, right? The union of those two probabilities, right? Now, in this case, I'm looking at this area in here. What does that area represent in there? It represents people that are both left-handed and both diabetic. And the way I might represent that is the intersection. And we symbol used for intersection is an upside down U. Right side up U is union, upside down U is intersection. So for intersection, I turn that upside down and say A and B, the intersection of A and B. That means people that are both diabetic and people that are both, and the people that are left-handed. Okay, so in the homework, you notice we ask you a bunch of stuff. Like, for instance, and the other thing that we say is, let's say that we're interested in, do another one here. Let's say we're interested, here's A, here's B, okay? And we're interested in everything that's out here, including B, except for what's inside here. What would you call that? Everything in the world except what's inside of there. That's the inverse of A. We call it the complement of A with a primary. That means not A. Okay? So if I showed you a Venn diagram and I shaded the areas I was interested in, okay, what would we have here? We'd have A, right? Probability of being A, whatever A stands for, diabetic, let's say. Okay, let me go up here. Okay. What about if I just shaded this part and not this part? That would be probability of being B, say left-handed or something like that. Okay, so now how about if I sheet? Oops. Okay, how about here? What is that? Oh, that's both. That's the intersection of A and B. Okay, now let's see. How about if I'm talking about this area in here? What am I talking about there? Well, it's B, but I'm not including the people that are both A and B over here. So that is, what is that going to be? That's going to be the intersection. Let me see. That's going to be the intersection of A, of B, and not A. Right? In other words, it's going to be B, but not including the part of B that's it overlaps into A. Yes.
So the dash next to the A.
That represents not A.
In the lecture, it has the C.
Oh yeah, okay. You can use I use the dash. So yeah, C. Same deal.
So you would say you can say not
The complement or not A. Yeah, same thing as not A.
Okay.
Yeah. Okay. So when you see these Venn diagrams, you see a bunch of them in the homework. Just take a look at them. Sit there, say to yourself, well, what is this really telling me? Is it part of A? Is it part of B? Is it an intersection? Is it excluding a part? And that when we're excluding a part, it usually says the complement. That means not A or not B. And I'll stick with C since Levi's using C. I'm going to stick with C for the rest of the semester.
Exclusion is complement.
Yeah. So, well, the not part of is complement. Okay. Okay, good. So let's move on from there. So we may dabble in this a bit more, but then what we did is we went off on a complete tangent, right? We started talking about diagnostic tests, and we're going to talk about diagnostic tests, but then we're going to come full circle back to probability, okay? Because we're going to discuss something called Bayes' theorem. Okay, so let's talk about this. Okay, questions so far? We comfortable with this so far? Yes, online? Okay, complement. Yeah, okay. Peter, yep. Peter likes complement also. He prefers that also. All right. So at any rate, so let's take a look at this. Let's think about this. Diagnostic tests, a lot of times you want an effective way to detect disease, right? Whether it's for right now Zika, right? There's a diagnostic test for Zika. I think it's a pretty elaborate test because they're having trouble keeping up with people that want to test on in Florida. Am I correct? There's a big issue right now in Florida. Like, there's so many people that want to be tested that the labs can't keep up with it. So it must be a rather difficult test to do. Let's say that you find you're developing a test for Zika, right? Well, what's important in your test for Zika? Well, first of all, it's got to identify people that have Zika, right? That's number one thing. You want to be able, somebody has Zika, you want to be able to tell them, oh yeah, you got it. That's that's the disease that you have. The other thing you want to do is if you don't have it, you want to be sure that you're telling people that don't have it, that indeed they don't have it. You don't want to tell people that don't have the disease that they do have the disease, because then they have to go for treatment and more maybe expensive or invasive treatment and so on and so forth, or additional testing and so on. So you don't want to do that. So we want to be right in both directions. We want to be able to tell people that have the disease that they test positive, that they have the disease, that test negative, that indeed they don't have the disease. Problem is that tests are not perfect. None of these tests are perfect. Okay, so some tests they call a gold standard. Like, for instance, if you were concerned about heart disease, what's the first thing a doctor would do if he's concerned about doing a physical and he's concerned that you might have heart disease? What's the first thing that he would do? The least invasive test. EKG, right? A resting EKG, right? What's the second test he would do? Put you on a treadmill, right? Do an exercise EKG, stress EKG. What's the third? And each one of these tests gets more difficult. What's the gold standard there? What's a test that pretty much defines whether or not you have coronary artery disease? It's a cardiac catheterization, right? They actually look at the flow in the arteries and so on and so forth. That's pretty much the gold standard. But you want to be able to, that's an invasive test. It's a dangerous test, invasive test. So you want a test that's less invasive, less dangerous, but you want it to be effective too. So we're going to look at our Zika test. We just developed it in the lab. We think we're going to make big money out of this test, right? It's going to be, maybe it's even that we're going to sell it over the counter or something like that. But it's got to work. Okay, so now we have a number of different outcomes. A lot of times when we have different outcomes, we assemble them into a table. Right now we're going to assemble them into a 2x2 table. We call that a contingency table. Okay, blood pressure. Oh yeah, Peter, that's good. I didn't even think of blood pressure. That's another screening test. Very very simple, non-invasive. Okay, so what are the things that might be in this contingency? Well, first of all, we have two possible test outcomes and two possible disease outcomes. You test positive or you test negative. You have the disease or you don't have the disease. Okay, so here's our test. Test positive, test negative, right? And here's our disease. You have the disease, you don't have the disease. So I'm going to take an imaginary population. Okay, let me draw a few other boxes around here so I can organize my numbers. I'm going to take an imaginary population. I'm going to say that population has 1,000 people in it. Okay, so now if I were to tell you that in Florida right now, that the rate of Zika is 10%. It's really taken off. This is a year from now. It's taken off. 10% of the people in Florida have antibodies for Zika infection. How many people out of those 1,000 would have Zika? If the prevalent is 10%, 100, right? Okay, so now where would I put 100 here? Well, if you look at this first column represents the people that have the disease that test positive, and the people that have the disease test negative. So the total is the total number of people that have the disease, right? You guys okay with that? Okay, so how many people don't have the disease? 900. Okay, so now let's say I test those 100 people, and I get it right on 80 of them, but I get it wrong on 20 of them. They test negative, 20 of those people. Okay, and on the among the people 900 people that don't have the disease, let's say I get that right 90% of the time. 810 people test negative that don't have the disease. That leaves 90 that do have the disease. Okay. Well, first of all, in terms of positives and negatives and false, true or false, what do I define this as? You test positive and you have the disease. What would we call that? We're going to call that a true positive, right? How about you test negative and you don't have the disease? It's a true negative. Okay, now the hard ones. How about if you test negative but you do have the disease? That is a false negative, right? Okay, and how about if you test positive and you don't have the disease. That's a false positive, right? Exactly. So how many people here test positive? 170 people out of this population tested positive. How many people tested negative? 830, right? Adds up to 1,000, of course. Okay, so now let's describe how good this test is. How good was it at what percentage of the time did it get the disease population right? 80 out of 100, 80% of the time. We're going to call that something called the sensitivity of the test. That's simple. That's what the sensitivity is the percent that you get that right? Percent that you identify people that have the disease. Test positive and have the disease. Now, what about people that are negative? I'm going to call, how often did we get, that happened 90% of the time, right? We only got it wrong 10% of the time, 90 people. 810, we got it right. 810 over 90 is 90%, right? I'm going to call that the specificity of the test. And what's the specificity of the test? That's the percentage of people that test negative that are negative. Okay, so in this case, the sensitivity is 80% and the specificity is 90%. Okay, that's really nice. If we were going to publish an article online, if we were going to publish an article, I need to check something out here. Here's my mouse. Oh, that thing's over there. Let me find my mouse here. Make sure everybody's muted there, because sometimes you get a little bit of crosstalk. Okay, so now let's say I take a look at this and I say to myself, if I'm going to publish an article on this, very nice. I tell doctors that the sensitivity is 80%, the specificity is 90%. That means a lot to them. They'll understand that. They'll know how to figure this stuff out. Public health professionals know what that means. Something that might be more relevant to people that are not public health professional is, gee, I just got back from the doctor. I tested positive. Do I have this disease? Well, is this a perfect test? No, it's not. Well, let's take a look at the likelihood that if you test positive, that you have the disease, right? Remember, we're looking at the total number of outcomes that we're after over the total number of possible outcomes. So how many people tested positive? 170. And out of that 170, how many of them really have the disease? 80, right? So only 80 out of, let's see what does that come out to? Oops, can't leave that on there. That won't work. 80 over 170, we know it's under 50%. 80 divided by 170. Okay, so the test is right 47% of the time, 0.47. So even though we tested positive, the likelihood that we have the disease in this test, which is not a bad test, right, 80%, 90%, is less than 50%. Right? This is called the positive predictive value. Right? That's the positive predictive value. So if you have a test that has a low positive predictive value, then gee, a lot of people go home and get, they get a positive test, and now, oh no, I have to go for more testing, and so on and so forth. It happens quite a bit, right? We use PSA for prostate, for diagnosing prostate cancer. We use Pap smears and so on and so forth. Now, you test positive, you wind up having to do more exhaustive testing, maybe even invasive testing, right? Or even treatment, right? So it's not nice to have a problem with the positive predictive value in the test. This actually isn't too bad. We're going to take a look at a version of this. But before I move on to that, how about how good it is at predicting negative tests? In other words, if you test negative, how likely are you to not have the disease? So I'm going to call that, what should I call that? Negative predictive value. And what's a negative predictive value equal to? It's the total number of people that tested negative is 830. How many of them were really negative? 810 of them were really negative. So it's 810 out of 830 people that tested negative really are negative. And let's see what the negative predictive value is. 810 divided by 830. A lot better than the other way, right? Almost 98%, right? So I'm going to round it off to 98%. So negative predictive value is 98%. Positive predictive value is only 47%. Kind of interesting that it would come out that way. Watch what happens when I apply this test. Let's say Florida got a lot of mosquitoes. I'm going to take this test, same test. I'm going to take it up to Alaska, use it in Alaska, right? Alaska, they have giant flies that bite you to death. They don't have mosquitoes, right? I probably got mosquitoes up there too. But let's to keep this simple, let's assume that they don't have mosquitoes in Alaska, or not many mosquitoes in Alaska, and maybe not the kind what is it, Aedes, the tiger ones. What are they called? The Aedes. I don't remember I remember the genus is Aedes. I don't remember the species. Anybody remember online? It's Aedes something. I think it's a tiger type, the ones with the stripes. Okay, so at any rate, so I'm going to take this same test. I'm going to take it in the population in Alaska. The test is the same. Nothing's changed. The only thing is, in this population, I think 1,000 people, in this population, the prevalence is 1% instead of 10%. Only 1 out of 100 people have Zika in this population. I'm still going to say sensitivity, the innate measurements of the test are the same. Sensitivity, it's right 80% of the time on that. Specificity, it's right 90% of the time on specificity, right? So the only thing that's changed is the prevalence in the population. So let's take a look at what happens with my 1,000 people. Out of my 1,000 people, how many actually have the disease? Well, only 10, because it's only 1% of the population. Well, if I get it right 80% of the time, 8 out of the 10 people will test positive. That have the disease will test positive. Right? 2 people will test negative. And out of the 990 people in this population that don't have the disease, let's see, 99 will test negative and will test positive, and 891 will test negative. I got that right? I think I got that right. Right? 90% of them will test negative, 10% of them will test positive, even though they don't have the disease. Okay, so let's add this up. How many people tested positive here? 107. Right? How many people tested negative? 893. So what's the positive predictive value for this test? Positive predictive value for this test is 107 people tested positive, but only 8 of them had the disease. So if you tested positive in this population, right, let's see, clear, 8 divided by 107, there's only a 7.5 or 7% chance. Only a little bit more than 7% chance that you have the disease. The test is the same. What changed? The prevalence in the population. And why is that happening? That's happening because when you test so many people who don't have the disease, you're going to get more false positives, right? So when you have a population where nobody has the disease, and you test them, then you're really going to get a lot of false positives. But if you have a population where half of them have the disease, half of them don't have the disease, you're not going to get as many false positives because so many more people are indeed positive. Okay, so keep that in mind. That's what happens with this stuff. Now, let's take a look at that positive predictive value.
So the prevalence is very
Right, exactly, right? The sensitivity and the specificity is innate to the test, but the prevalence is what really can cause the positive predictive value to table in the homework. I think there's a table in the homework. It might just be in the presentation. I'll go in here. I know we got one in here, I think. I'll make my own table up. What the hell? I'm flying without a net anyway. I might as well continue. Okay, so let's say I were to ask you, I'd say to you that, let's see, I'm going to make up another contingency table. And in this contingency table, we have, we think of something that has different groups. We're going to have baseball players. We're going to have soccer players. We're going to have football players, American football players, and we're going to have tennis players, right? And I'm looking at whether or not they are married or unmarried. Okay, so here's my population. Okay, and I'm going to say, let's see, there's 20 here and 10 here and 10 here and 30 here. And over here, there's unmarried, there's 5 and 20 and 10. Let's say, how many people I got here total? I've got 20, 30, 40, 40 and 30 is 70. And here I've got 10, 30, 40. So there's 110 people here total. I'm going to change this. I'm going to make this one 20. So it adds up to 100. We have 100 people in this population, right? What's the problem? If I pick someone from this population at random, what's the probability that they're a baseball player? How many baseball players we got? We got 25 baseball players out of how many? Yeah, out of 100. So it's 25 out of 100, or 0.25, or 1/4. Okay, guys online looking at that too. Okay, let me make sure the chat box is open here. Yeah. Okay, yeah, I changed it on you, Thomas. Okay, so at any rate, so it's 25 out of 100. Okay, what's the probability in this population that if I pick one random person that they're married? Well, how many people in this population are married? 60 out of 100, so the probability is going to be 60 over 100, or 0.6. Okay, now, given that they are married, what's the probability that they play football? Oh, wait a second here. Given that they're married, I'm only looking at the married players here, right? Okay, how many of the married players are football players? 10 out of how many? 60. So the probability is going to be, probability of being married is going to be 10 out of 60, or 1/6. Right? That's probably. Now, what happened there? I placed a condition on it. That's what we call a conditional probability. What's the probability, given that they're a football player, that they're married, that they're also a football player? I could have said, what's the probability, given that they play soccer, that they're unmarried? So that would be only 5 people out of 15, be 1 in 3. Because the condition there is that they have to be a soccer player. So I'm only looking at soccer players. Conditional probability. Remember we were just talking about positive predictive value? Another way of me describing positive predictive value, what's the probability that you have the disease, given that you what? What's the probability you have the disease, given that you, how about online? Go ahead, test positive, right, exactly, right? So in other words, the positive predictive value, another way of saying that is the probability that you have the disease, given that, and usually they do that with a slash or a pipe, like straight up and down, that you test positive. That's the positive predictive value. 8 out of 107, right? But you see the deal here is it's a conditional probability. The only people we're looking at is the people that tested positive. So probably you have the disease if you're in that 807 that tested positive. Okay, conditional probability. So for the last thing I'm going to talk about on this, I'm going to stretch this out a little bit further. And I'm going to use something called Bayes' formula, Bayes' theorem. Okay, and basically it involves conditional probability. So I'm going to look up, I'm going to see if I can't dig up the formula so I don't have to write it out from scratch. But it's basically describes a situation where you have a conditional probability. That's what I have to do to find it now. Okay. You know, I got 8,000 untitled folders inside an other untitled folder, because every time I do a session, I have to clear off my desktop, and I put it in an untitled folder, and the next shove it into something else. And pretty soon I have layers of untitled folders. Until eventually, believe it or not, I've gotten so bad that when I do a search, when I find a file that's inside an untitled, it's so far down that the operating system won't let me retrieve it. I have to go to the folder first. That's pretty bad, right? Let's see. Conditional probability. I think it's going to be a formula. Here it is. That's it right there, I think. Yep, that's it. Okay, I'm going to drag that in here. Oops, that's not what I wanted to do. Did it take it? Is it? Fine. Okay. So I'm going to make this bigger. Okay, so this is going to be my formula for conditional probability. And what do I have here? On the top, positive predictive value is the probability that you have the disease. Well, what's the probability you have the disease? It's the sensitivity times the prevalence, right? Probability that you have the disease and you tested positive is going to be the sensitivity, and the prevalence is the number of people, the percentage of people who have the disease. Let's say it's 10%. And the sensitivity is the likelihood that you're going to get a positive test for them. So on top is the percentage of people in the population that have the disease and test positive, right? That's the top part of our equation. So what goes on the bottom part of our equation? All of the people that tested positive, whether they have the disease or not. So what do we have? We have two parts here. The first part is the same as the top, which would make sense because we want to include the people that have the disease and test positive and people that don't have the disease that test positive, because we want the bottom to be both the false positives and the true positives, all the positives, to get our ratio right. Okay, so the sensitivity times the prevalence is our true positives, our people that have the disease and test positive. Well, now we have to have the people that don't have the disease that test positive. Okay, so what percentage of people don't have the disease? Well, the prevalence is the percentage of people that have the disease. 1 minus the prevalence is the percentage of people that don't have the disease. So that would be, if the prevalence is 10%, that would be 90%, right? And now I want to get those 90%. I want to know how many of them tested positive, that 90%. Well, the specificity tells me the percentage of people that don't have the disease that test negative. So 1 minus the specificity will be the percentage of people that don't have the disease that test positive. So I'm going to multiply 1 minus the specificity times 1 minus the prevalence, and it's going to give me the percentage of people in this population that are false positives. So I combine that with the true positives, and I got my equation here. Let's test it, see if it really works. I'm going to use the same. Should I use 1% or 10%? Okay, use 10%. Okay, good. All right, so I'm going to work this out now. Let's see if I can't get this to work. See how lucky we are today. Some days this works out good. Some days it don't work out so good. Okay, let me bring this up here. I got to click on that, and I'm ready. Okay, so sensitivity times the prevalence. What was the sensitivity of my test? It was 0.8, right? 80%. And what was the prevalence? 0.1, right? 10%. Okay, we good so far? Okay, I'm going to put that over the same thing. This is the percentage of people that are going to test positive that have the disease. 10% of the population, 80% right, you're going to get it right 0.08 times, right? Okay, so that's going to be down here. It's going to be the same thing. 0.10. Plus, what's the specificity of my test? Remember what it was? It was 1 minus the specificity. I think we said the test was 90% accurate on giving us negatives, times 1 minus the prevalence. Prevalence was 10%, so this is 1 minus 10%. Okay, so what do we have here? We have 0.8 times 0.1 is 0.08, right? Over 0.08 plus 1 minus this, 1 minus that is 0.1, right? Okay, and 1 minus 0.1 is 0.9, right? So 0.1 times 0.9 is 0.09. So we got 0.08 divided by 0.107. Numbers look familiar? What does that come out to? Okay, trust me on the math here if I got ahead of you on the math a little bit, because we don't have that much time left. Okay, so 0.08 times, divided by 0.107 is equal to 0.74, so on and so forth. Whoops, 0.747. Let's go back to see what it was when we calculated it the other way. 8 over 107, same answer. Okay, so if I gave you just this information, if I gave you only the sensitivity, the prevalence, and the specificity, you should be able to calculate for me what the positive predictive value of the test is. Okay, and if we take a quick look at the homework, let's see what we got. Let's go take a quick run through the homework. You actually got 10 days to do the homework in 610, 6 guys in 6. If anybody here is from 611, you have a little less time, but because you have a test that comes up sooner than they do in 610. But where was I here? Let's see. I was going to pull up this. If you look at the homework, just a quick preview of the homework. So we'll have another session before we have. Are we closed on a Thursday? Is there a problem with Thursday? One of these weeks, like Thursday is a Monday schedule or something like that. Not yet. Later on. Not next. Not after. Okay. Good. No problem. Okay. So let's see. So what do we have in the homeworks? In the homeworks, we got, prevalence diabetes, 10%, 3 randomly selected people. We just did that, right? So you should be able to take care of that. Then you have different versions of that. Okay, here's our Venn diagrams. You got to choose which one that's represented there, right? A intersection B, A union B, B intersection A prime. I used that other notation, right? Trust me. You see A prime, same thing as you see. Okay. Okay, the prevalence is a condition. Like I used it. Did I still talk about cooties, or is that like?
You said A prime is the same as one?
Not A. A complement. Sometimes you'll see AC. Sometimes you see A prime, but it means not A. A complement, not A. But is that like a thing from the 50s? They don't talk about cooties anymore. Is that? Cooties. Exactly. It's still around. Huh? Okay, if you're like in 6th grade, right? Yeah, okay, good. That's still around. That hasn't disappeared. Okay, cooties is still actually. There's still a prevalence of cooties around. So that's good. I'm glad to hear they haven't eliminated like polio, right? Polio's gone, but cooties are still here. Okay, so at any rate, so we have an example of a test that involves cooties, and then you can do various calculations to calculate the specificity, sensitivity, and then finally the last problem is very similar to what we just did, except I think the percentages are a little bit different. So you guys should be able to go home to work. You should really consider, since there's 5 of us here, there's how many of us? There is, I lost track here. But looks to be about 4 or 5 of us online. So 9 of us. The 9 of us should go home and do this now when it's fresh in our heads and stuff like that, rather than put it off for a week and a half and then do it the last minute and not remember and have to play the video and so on and so forth. You know, I one of these weeks, maybe next week, I'm going to try and take prep the videos so that there's like when we talked about Venn diagrams, just take that as a 10-minute video. And when we talked about this, just take this as, like Bayes theorem, this other, break it up into 10 to 15-minute videos or something like that. And what I've been doing, playing around with a little bit, is like giving you timestamps on some of them. So, if you're interested in this, you can just go straight to 11 minutes or something like that. So it's a little bit more challenging to break it up into smaller videos. But I'm going to give that a try. And then maybe I'll do a survey on whether people just rather have it as one video so you play it continuously, or if you want to broken up into smaller segments.